I'm going to try this one more time. Take a picture of this or go to my Moodle page and find the PDF of this that I've made. Let's try this one more time here. So for part A of this problem, they gave you the electric field 10 centimeters away from the center of this whole setup. I'm going to use that value, electric field and distance, to figure out how much charge is enclosed in part A of this problem. Okay, if you look at this here, 1,780 newtons per coulomb was your electric field. I set that equal to K, Q enclosed over R squared. Okay, so when I go through and I do the math, I solve for Q enclosed, I end up getting 1.98 times 10 to the negative 9th coulombs. Let's call that nanocoulombs. I put a negative out in front of there because if you go back to the paragraph of that problem, you'll see that that paragraph said that the electric field was radially inward. So inward is implying that's a negative charge. So now that we've found the Q enclosed by a Gaussian sphere that's 10 centimeters in radius, I can go back to the picture here. I constructed a blue dotted line to represent the enclosing Gaussian sphere that happens to have a radius of 10 centimeters. And the charge that's enclosed by that Gaussian sphere is all the charge on the insulator. The other valuable information that they give you is the electric field at 58 centimeters from the center of this entire setup. They tell us that electric field, they tell us the distance. Again, we can use electric field equals K, Q enclosed over R squared. So I want you to pause for just a second, check the paragraph again. You'll see these numbers are in there. Type this into your calculator and see what you come up with for the Q enclosed by our Gaussian sphere that's 0.58 centimeters, 0.58 meters. All right, welcome back. I'm hoping that you took a minute and you found that the answer is 5.61 times 10 to the negative 9th coulombs. And we'll just call that nanocoulombs. I called that one positive because in the paragraph it said that the electric field was radially outward, which again implies that it's a positive charge. Electric field is out away from positive, inward toward negative. If we come back to the board here now, and we look at that Gaussian sphere that we're describing, that Gaussian sphere has this radius of 0.58 centimeters, and you think about, well, we just solved for Q enclosed. What is the enclosed charge? That value that we just solved for, that 5.61, is enclosing not only the insulator, but also the conductor together. So now we got to do a little setup to figure out how much charge is on the conductor itself. Okay, so when I go over to this equation here now, my Q enclosed is just another way of saying net charge. So my Q enclosed equals the charge on my insulator plus the charge on my conductor, and the numbers that I plug in are now set up so that I can solve for the charge on my conductor. Notice I've got that positive Q enclosed, negative charge on the insulator. Thinking I'm going to end up getting a positive charge on that conductor. Okay, let's add this to both sides. All right, so I just went and I added this to both sides. You end up getting some math that shows that 7.59 nanocoulombs equals the charge, on the conductor. Okay, so that's everything that's on this conductive circle out here. Let me put in that positive 7.59 nanocoulombs. Now this is where the last part gets a little bit weird. We just figured out how much charge is on the conductor, but they want to know what's the amount of charge on the inside edge of that conductor and on the outside edge of that conductor. I'd say we've got part A and B done. The final two parts now are going to be this. Let me grab a hold of a new marker here. Here's where it kind of starts. Since this is a negative 1.98 nanocoulombs, that has the ability to influence the positives and negatives in this conductor. Conductor has charges that can move easily. So I would say that this is capable of attracting positive 1.98 nanocoulombs to that inside layer right there. This negative attracts the same amount of positive. So it turns out that of this 7.59 nanocoulombs that's charged up on the conductor, 1.98 of that is on the inside edge. The rest of the 7.59 should be on the outside edge. So you have to help me with a little bit of math, but you're going to find out that this is going to be where the rest of your positive charge is. So wrapping this up finally, the rest of that 7.59 nanocoulombs is 5.61 nanocoulombs, shows up on the outside edge of this outer conductor. Okay, so all of that net charge, some of it gets attracted in toward the negative insulator. The rest of it is going to stay out at the outside edge. The part that's slightly intriguing about that is that when we solved for Q enclosed at 0.58 meters, we found that the answer was 5.61 nanocoulombs was everything that was enclosed. What you'll find is that that total enclosed charge is going to end up on the outer surface of a conductor. Find that a little bit intriguing. Then our answers that show up on this answer key here match up pretty nicely with what we've just solved for.